So we are developing the model for that, right. So there are several minor variations you can make to that model to make it more accurate, and usually that is a trade off, right. How accurate you want. If it gives you reasonably good results with the base model, then that is fine, but sometimes you will have inaccuracies also, so you have to be careful with that. Okay, so the model you remember from last time, so I will not redraw that. We said we look at the two parameters, right. So throughput, right, per user, we call this as gamma. So throughput of the user is, so it is when the user is in state either 1 or 2, right. So that is when you are transmitting, and the probability of success is just PS. That is your user throughput. This is my guess, right. You should go back, then plug these numbers, get the values, then go back to your simulation that you did for part 3 and see whether it actually makes sense, right. 3 users, 10 users, look at whether the numbers are actually matching. So then the system throughput with m users is simply m into this, right. And the delay we can calculate by simply computing E of n, that is the expected number of packets in the system, right. If you are in state 0, then there is no packet, state 1 or 3 there are there is 1 packet, 2 and 4 there are 2 packets, and so on. So now we know the steady state probabilities, you can simply compute that, and therefore it will be simply, right. So this is, no, lambda will be the effective throughput of the system. So mu is what we will be looking at, mu is the effective arrival rate to the system, because mu is the effective throughput, right. So we can check it out, because lambda, we can have very large lambda, but what the system is seeing in terms of departing from the system is the effective arrival rate for the system. But anyway, that's how I did it. I may be wrong, we will have to go back and check whether lambda is actually the value, but my paper I said mu and or gamma, and right. So state 0 there are no packets, so state 1 there is 1 packet, so 1 into V1, state 2 there are 2 packets, and so on, right. Isn't that how we number that? So state 2 is transmit with 2 packets, right, because I left my sheet there, so I match which is, and then V3 plus 2 into V4. So that gives you an approximate analysis for Aloha. You might ask, what is the point of this, right. Aloha I can implement in 2 pages with any simulator, so why go through all of this? So that is when we used to remember our first class, first set of classes, that is for cross validation, right. How do you know your simulation is correct? You have some other model to validate it. So this is what cross validation comes in, and how do you know model is correct? You look at the simulation results, and then finally at some point the two reasonably converge, you know that we have some commonality, okay. So that is the Aloha model, and in fact this model I actually developed for a system with multiple channels, where not just one channel, there are multiple channels that will be shared among users, and we have this fixed receiver model and so on. So that paper actually look at it, which I have now put on the website, Synchronous paper. The model is the same, there only thing is the PS calculations will change because of multiple channels, for example, right. There are several variants. This is a WDM local area network with multiple channels. In that variant we looked at fixing the user transceiver channel, for a user will receive on a fixed channel. So if I want to talk to some user, I have to send on that user's home channel, so called, right. So therefore the load will be evenly distributed among all the C. In ideally it should be, if there are m users, then they have and there are C channels, and m is larger than C, so m by C users will be sharing a given channel. So the load per channel is m by C.
Suppose everybody moves to some particular user.
Yeah, for unbalanced traffic, imbalanced traffic, or whatever, yeah, then the channel will have a lot of collisions. But we cannot do much with a single transceiver. We have only one receiver at a node, right. It is like a base station. The base station can have multiple transceivers if it wants to, but a single transceiver model, it is not suitable. You will have collisions on the channel. Okay. Other questions?
So this here V1 is equal to n by
yeah.
That V1 will be divided by the throughput also.
Which one?
The 1 V1 plus 2 V2 plus 1 V2 plus 2 V4.
Delay. Yeah. Okay. So now Aloha we have done, right, this is on a user perspective, and we have now let us we have seen TDMA, right, with that other day, which is also your last tutorial that you saw, right, how we can compute TDMA performance with that model. Now I say I want to do TDMA with a Markov model. Okay. So let us try to develop the TDMA with Markov model, and knowingly or unknowingly I left my TDMA model at home. So we will have to now develop that from scratch, right. So how do you model a TDMA behavior of a particular user? Okay. So the system description is as follows: I have m users sharing one channel, and each user is lambda packets, right, per unit time, per user, and this is broken down into slots. So there are m slots, every user has his or her own slot. We saw this a couple of weeks ago or last week. So now if you want to model this as a Markov, not exactly Markov, it will be semi Markov, but let us try to model this and then we will see what the definition of it works out. Okay. So let us try to figure out the states of this model. Again this is looking at the each user's queue, right. So I am looking at the user queue to which packets are coming at rate lambda, and there are several such queues. So I am basically modeling the state of the system, state of each transmitter. Okay. And we assume that this is a major assumption that all the users are identical, therefore right, just looking at one user's queue is representative of the system behavior. Okay. So let us start with one state, state 0, what will that be? Idle state. Okay. So this is S0, idle state. Okay. So I will be in idle state for some time, right, for a while. So I can do the self loop like last time, right, where in idle state in every slot the probability of generating a packet is beta, beta is 1 minus e power minus lambda. So that same definition is holding, but now let us say that I do not want to, right, I do not want to do this self loop, I want to eliminate the self loop, right. So therefore the time spent in this state S0 is no longer unity, it is some number, right, it could be, it is a random number, in this case it is a geometric process. So we know it is going to be 1 over beta is the time that you spend in that particular slot. Okay. So from S0 I will go to what state? I will go to two states S1. Okay. So what are the two possibilities that I can have?
It arrives exactly when the slot reaches, so you will be able to send the slot packet.
So I was in the previous slot, right, I had two slots 0 and 1. Beginning of slot 0 there was no packet in the queue, so waited, just sometime in between before slot 1 started the packet has arrived, right, therefore it can be sent right away, so there is no waiting there, right, that is one possibility. Okay. So we will have one transmit, this is this is my transmit state. Okay. So with this is S1 transmit state with only one packet in the buffer, right, there is only one packet. So from S0 I can go to S1, or what is the other possibility? I will go to the wait state, right, so there is a wait state here. This is waiting for your turn to arrive on the channel. Okay. So now for each of these states I will also list their so called sojourn times. So basically the average time, this is actually the mean sojourn time, right, this is the mean sojourn time in each state. It is no longer unity. In this Aloha case it was nice, but in this case it is the way that I am modeling it, right. So what is the amount of time spent in this state? 1 by beta, geometric process, right. With probability beta I will leave that state, so that is your probability of success, so 1 over p, so that is 1 by beta. Then what is the probability of going to state S1 from S0? Yeah, I am leaving if there is only a packet arrival, so that beta will not, it's either 1, alright, it is 1 into something. What is I am leaving the state only when there is a packet. Yeah. So what? So S0 to S1, what is the probability of that?
1 by n.
1 by m, right. So there are m slots, and exactly in the beginning of your allocated slot your packet has arrived. There is a packet in the queue. That is with probability 1 by m, right. So with probability 1 by m, I will go to this. This is actually different from the model you will see in the paper. Model actually I do not do S0 to S1, I send everybody to wait state. So that is why if you look at my graphs there is a gap between the simulation and the analysis, always you will find a distinct gap, but we can be more accurate by looking at this one special case. If the packet has just arrived, that is the problem, there are m slots, so packet can arrive in one of those m slots, right, and since all slots are equally probable, arriving exactly in that one slot that is allotted to you is 1 by m, and this is m minus 1 by m. Okay, so this is my transfer. So then it is my allotted slot, so therefore what is the so this is now TDMA, therefore I will simply spend 1 unit of time when the packet is successful, there is no question about that. Then after that what happens? So once I send a packet in a slot, right, two possibilities, a new packet has arrived in that slot when I was sending, or there is no packet at all, right. Okay. So if the no packet has been generated, then where do I go to? Go back to idle state. So that is this transition here, probability beta bar. So from S0 to S1 my slot I sent. In case a new packet has arrived, then I have to go to a state, another wait state. We'll okay. Let us. We want to do this wait state first. No, let us. There is another wait called synchronous wait, or full wait. We used to call that. How long will I wait in that state? Because my allotted slot is over. I need to wait for
m minus 1.
M minus 1 slot, right? So therefore, this is going to be going to we'll call this S2, S3. Okay, so in synchronous wait,
Packet has arrived.
yeah.
Then that will be like that also does the sync wait, right? Even from idle.
Yeah, yeah, we'll come to that. So now if I just look at this sequence, packet comes, my slot, I send, another packet comes, I am going to this full wait state, and the time for this one is m minus 1, right, because I have to wait m minus 1 slots for my slot to arrive, for my chance to arrive again. That is the first part. Okay, this is the sequence so far. Beta's probability of one packet arriving in one slot. Because it is lambda packets per unit time and slot is 1, right. So this is one sequence of packets, right. Okay. So far so good. Now S2, what is the time spent? Yes.
So by synchronized wait we mean that it has gone in one of these slots. Now it will wait for
Exactly m minus 1 slot.
Exactly, then it has to
Yeah.
come to that slot only. That's why it is called synchronous.
Synchronous wait, yeah.
In the normal
Wait, it is not. It is it's a probabilistic wait. So here, now let us try to compute this, right. So what is the sojourn time for this state? So I am coming into wait state because I missed my slot. Okay. So now I could actually have S1, S2, S3, S4 up to S minus 1, right. I could have a whole sequence of states by saying that S2 I wait 2 slots, S3 I wait 3 slots and so on, or S1 I wait 0, S2 I have to wait for 1 slot. I could have an entire length of right per state, because it's only m, I can easily do that, which I didn't do. No, this is a uniform random variable. So the time spent is either 1 slot or n minus 1 slot, right. So the average time, so now we are only looking at the average time spent in this waiting state. So what is the average waiting time? Either because I just missed my slot, right. So what is the, I would have wait for n minus 1 slots, or I just came, there is only one slot left to go, right. I was in the previous slot before my allocation. So this is m by 2 and this is no mean, right. So it is a mean time, mean waiting time. So again a set of states, transitions between the states, the only difference is now the time spent in each state is not exponential nor geometric, that is the only thing.
So why can't you explain the transition probability between S0 and S1, S0 and S2? Why it appears with that? Because I am surprised why beta doesn't appear in that.
Because I have made my
S0 is idle with
time.
Nothing, right?
This
S0 is
if
idle
I
with no
want,
packets.
I can make this self loop with 1 minus beta and this will be beta by m, beta into 1. But if I am saying that the time spent in the state, the average time spent in the state is simply 1 over beta, I am basically stuck in that state for some period of time. That is the sojourn time of that state, right. Yeah. So rather than do a per state per time slot transition, I am simply doing it as a the average time spent in that state.
Yeah, but no, this transition should also involve beta, right?
That because your tau naught equals 1 by beta. So therefore, if you are leaving that state, it means there is a packet arrived. It's a geometric process, right? No packet, no packet, no packet. Finally, a packet has come. So how long do you stay in the no packet state is 1 by beta. Okay. So in our, I'm sorry. It is not Markov anymore. It is a semi-Markov model. Okay. That's if it is yeah. So this will be a semi-Markov model. Right? If I replace that self loop with this sojourn time. Now in this case it is nice. This is geometric, which is memoryless. But in this case, this is not. Tau 2 is not geometric. It's a uniform random variable, right? Anywhere between 1 to m minus 1 plus 2 is possible. Therefore, the time spent is here, and this is a fixed, right? This is a deterministic random variable technically, right? We will spend exactly m minus 1 slots. So you have all kinds of states here, and this is of course 1, which is also deterministic, right? But it's like our regular Aloha model where all slots are unit time. So far, with me? Okay. So now where do we go? So now I have come here, right? I have spent my wait time. So now I have to, I will go to transmit state. So it is my chance to send, okay? But will I always go to S1 or should I need yet another state? S1, there is only one packet in the queue. It's possible that while I was in S2, one more packet might have arrived because there is m minus 2 slots, right? So therefore I need something else. Okay. So what we have done is we have defined think theta 1, theta 2. So I will define theta 1 as, it's not consistent with my beta definition, but unfortunately my paper has this irregularity there. So this is e power minus lambda delta 2, which means no packets arriving in tau 2, sojourn time of 2. Therefore with the probability, again I called theta 1 even though I am coming out of state 2 first, okay, and this is 1 minus theta. So both are transmit states, and again with numbering the paper might be different. I might have renumbered this 3 and 4 differently. So we will just use this. My paper does not have this 1 by m business and all that, slightly different model, but you should be able to get the flow. So from here to here, this is the probability theta 1 1 minus theta 1. Okay. So the sojourn time is again 1. Then from synchronous wait, I came there because I started off with having only one packet, right? Because I was in S1 state. There was only one packet to begin with. In that one period of 1 unit of time, yet another packet came, but that packet is already finished transmission. So I am arriving here with only one packet in the queue, but during this duration, it's possible that one more packet might have come, right? It's possible that one more packet might have come. So I would then move to either here, right? I will again have to define theta 2 So this is 1 minus theta 2 and this is so while in synchronous wait state no other packet came, I go back to transmission with only one packet in the buffer. So that is theta 2 probability. In S3 I might have one packet or two packet. So if I in the duration of m minus 1 slots, right, I might have had one more packet, in which case I have to go to S4 where there is one packet being transmitted and one packet waiting in the queue. For the first packet is where I am saying m minus 1 slots, so I am going to my assigned slot. So from 1 I go back to slot 1, I go to slot 1. The second packet has to do synchronous wait again. From transmit I have to go back, so that link we have not yet drawn. If I have two packets in the queue, first packet is being sent, there is no room for the another packet, even though a packet might come, it is going to get dropped, right, because of the fact that I have only two buffers. So I have finished my top packet, whatever packet comes is simply going to be dropped. At the end of the slot, what is my state? I have another packet to be sent with waiting period of m minus 1 slots. I have to wait for the m minus 1 slots for my next chance. Make sense?
This packet waiting time is m minus 1 because it has to wait exactly m minus 1 slots.
Yes.
Now when this packet is in m minus 1, another packet will come to S3.
Yes, that is what the S3 to S4 arrow is showing you. See, S3 to S4 is probability 1 minus theta 2. If no packet has come, then there is only one, right? You are going to S1. S1 is simply transmission with one packet in queue. S4 is transmission with two packets in the queue. So from S3 I go to either S1 or to S4.
But that either tau 4 then 1 will not be consistent, sir, because both packets will not have only 1 unit.
No, there is only one, always only the head of the queue is being sent.
But second packet will be in that queue.
Second is coming back, see my S4 to S3 there is another loop which is always 1 because I have to go and wait for the second packet, right. There is no probability because with there is only one way I can go. I simply have to go back to state S3 and wait for m minus 1 slots for the next packet in the queue. Then that packet, during that period if one more packet comes, then I come to S4 or to S3 and so on. So the best way is to take this model, right, feed it into your program 1, just observe the sequence of states and see how the system is moving, right, not just steady state, actually use the emulator to see how it moves from state to state, right, print the state at every unit. We can do that, right, in your emulator you are doing that, what is the first state, what is the second state and so on, right. So simply keep printing the states as you are going along and you will find that the system has to go through in this particular mode. That is one way. Other is to implement this in the simulation and see how the simulators, right, what is the state change for a particular packet queue, what are the states it goes through. Any other transitions that I have missed?
Can you just explain the T2 once again?
This fellow, T2. T2 is empty queue, packet has come, and if I miss my turn, right?
It's m minus 1.
M minus. So just miss my turn, I have to wait for m minus 1 slot, right? Or I just got the packet before just one slot before my expected slot. Then what I can do is I can do 1 over m here and send it to S3 and then do m minus 2 by m, then this will become m minus 1 by 2, right, m minus 2 plus 1. So that is why I said this S2 can be blown up into as many states as you want, one of which will be S3, right. If you want to have a full blown expansion, I can have S1, S2, right, I came in the first slot, I came in the second slot, third slot, fourth slot and so on, which is fine, it is nothing wrong with that, it is a finer grain of states. So you will have more states in the system trying to capture every possible, so that will be a more accurate model. That will be your assignment 3 because my graphs have this problem, right, there is this big gap between, whereas this one, so we are always wondering with this, right. So this accuracy problem is because this wait state S2 is not an accurate representation. So this is the kind of trade off one has to do when you are developing models. Sometimes if you want to describe a model, and in this case it is a simple system, sometimes there will be so many such combinations, you will go into a combinatorial explosion of trying to all possible combinations is a state, it becomes a problem. So you try to condense some states into a single state, you do some averaging, the averaging will lead to errors, right, there will be approximations and that is something, but if you just want the approximate trend, I will show you the kind of graphs that Okay, before you look at that, so now is that question clear? Why we have m by 2? It's basically half the channel, half the frame that you have to wait.
The idea of S4 where you put T4 equal to 1.
Okay, I will show
what
you.
What does S4 mean?
This is simply the transmission state. See here, there is only one packet in the queue. S4 is the scenario where there is one packet being sent, this packet is waiting. There are two packets in the queue. Say this is simply the transmission time, that is all. One slot is in your, these two are the transmit states. In S4 there is only one packet in queue, sorry, in S1 there is only one packet in queue, in S4 there are two packets in queue, but you are only sending the top packet at the head of the queue, which is on your time. Right. So this is again, this is how you will start doing a model, and you will find that you will sometimes make some erroneous assumptions. For example, that when I was doing this, the TW this state is this state was also tough. This one was easy. This is simply m minus 1 by 2. This state, because I was doing this multiple channel thing, was much more complicated, because when I am in a particular state, I have sent my packet, right, then depending on what the next packet's home channel is, depending on the receiver of the next channel, I can either wait 0 slots or 1 slot or 2 slots and so on. So I ended up calculating that expression 1000 times, right, summation over this, summation over that, and it's every time there is some intuition, but half of it is also guesswork, and you simply say, will this work? If it works, then you just stop at that point, right, then you say, okay, I think my intuition is correct. So that difficulty is there. In this, for a single channel case, it's very simple, it's always m minus 1. Okay. So these models will get refined, and that is why you need some other validation technique. Okay. So we have covered, right, every state has a probability of 1, right. And if you look at the follow on paper for this, which we figured that what, I can make even B buffers, not just 2 buffers. I can extend this whole thing into up to B buffers and simply generate the same set of equations I can do. Only thing is I need my, instead of theta1 I will have a family of thetas, right, one for 1 packet in a slot, 2 packets in a slot, 3 packets in a slot. Depending on that, my queue length will also keep on increasing. We will put that for the final. How about that? I will make you look at that and derive that for the final. So that is the basic model. This is not powerful, this is okay, yeah, so this is there are situations where so we haven't yet, right, so this is an example of a semi-Markov model. There are scenarios where you try to model where the time spent in the states is not memoryless, right. If the memoryless property is not there, question is, can we use the same property, right. So the way we get the probabilities is, so we will first find out the visiting probabilities, okay. So the V that we calculated before in the case of that DTMC, right, is also the steady state probability. So we solved this, right. So with that same transition matrix, we can come up with the transition matrix, right. We can compute the V, which is now the visiting probability. It is not the steady state probability of being in a state. To go to the steady state probability of being in a state, so the steady state probabilities of being in state I is now Pi. So that is simply Vi tau I divided by so this is the steady state probability, right, of being in a state. So the probability matrix, transition matrix will only give you the visiting probability of each state, but then you also have to look at the time spent in each state. Effectively, to get your Pi you have to do this. So now you will get your Pi in 2 steps. And in this case there is no iteration, unlike the previous case where, right, P of S depended upon sigma. In this case there is no such iteration, it is a simple set of equations, right. because there is no dependence on in none of these would any of these variables depend upon, actually we no, this is fixed right, no, so there is no real dependence. I don't know why this keeps flickering, so there is no need for iterative process on this, but you can verify that later. Okay, this particular system the time spent is not Markovian, so it's but you can still use this same approach to get to the PIs, the steady state probabilities you can get. Then you will have to have a more complicated formula for finding out the tau 3, which will be an approximation, and that will lead to errors in your final results, right, it will not accurately model the system.
States you have,
The more accuracy, right, in this particular. So you try to aggregate states, then you try to aggregate the waiting times or the sojourn times, and that leads to errors. Okay. So this is the first step. So I have computed the steady state probabilities, right. Now let us try to compute the throughput of the system. What is throughput of the system? Throughput per user. So what is the throughput? It's simply the fraction of time spent in the two transmitting states, which was P1 or P4. My paper will say P2 I think, but you know how to figure it out. So P1 or P4, and there is no question of success of every packet is successful as far as the MAC protocol is concerned. Errors might happen because of bit failure, bit errors and so on, but if you send, right, this is your allocated start. So P1 plus P4 is this. So that was easy enough. Now second one, right, what is the number of packets in each state, right. So the number of packets in the queue in state yes, some cases it is easy, some cases it is not easy. S1 is 1, S1 and S4 are easy, 1 and 2, S3 I have to spend some time to figure out what is the probability of having that a packet would have arrived. So S3, S4, S3 and S2 require some extra computation, because I started off in S2 with S3 with one packet, sorry, in S2 with one packet, right. S2 is my that wait state of length m by 2. So what will that be?
S3 could be
1 is there, 1 plus probability of there being at least one packet, right. So basically 1 plus 1 minus theta 1. In this case, in other case is 1 plus 1 minus theta 1. So 2 minus theta 1, 2 minus theta 2, right. What is the probability of being at least there being at least one packet generated in S2? 1 minus theta 1. So now I can compute that, and theta 1 is again fixed, yeah, there is no interdependence on something else, right. So this is the way that I can, right. So this is, I am going to ask you to verify this. There is one packet in the queue, probability of yet another packet coming in the duration of that was plus. So then my usual delay formula will be E of n divided by, right. So delay equals so now we have 3 models for both SA and TDMA, or at least 2 we have seen and one simulation that we will see next. That is our next validation thing. Did I get my S3 this? In S3, right, the probability of I am already having one packet in the queue, I will have 2 packets, right, with there is a with probability 1 minus theta 1 I will have, right, this is the expected number of, it is 1 minus theta 1 into 1 plus theta 2 into 0, right, therefore it is simply 1 plus 1 minus theta
So shouldn't we take the time average of it? Like 1 minus theta 2, the second packet might come at any point of time.
It's again, I'm just right because it's a Poisson process. I'm saying what's the probability of being at least one packet, right? Basically, there should be no more than one packet, because more than one packet also the system will have essentially will go to a value of 2, right? So I'm just using one single value instead of saying right. Yeah, packet. This is the duration. Your Poisson probability of trying to get at least one packet in the duration is 1 minus theta 1. 1 minus no packet, right? Okay, so that's our first set of introduction to all these different models.
How that VP equal to P comes up in this VP equal to V.
That I never really looked into. I just took that as an expression and just left it.
I don't think in this case we can look at it like the previous thing. The previous thing, multiplication by
P was the probability set of probabilities in the next.
This P is that transition matrix, right?
Yeah.
So therefore, you can do that. So you are essentially getting the fraction of time that you are going to visit those states. But since the time spent in each of the states is going to be different, which is that it's more or less like the reward function is what we are trying to do. So tau is the reward function for being that, and how does that equate to steady state probability? I have never really thought about giving an explanation for that. I just took that as granted. Okay, so now we will slightly change gears to look at simulation. Okay, so I will introduce a bit of discrete event simulation to you.
we are getting S2, that is mean waiting time for one packet.
Which is one?
Tau 3 what we are
Yeah,
calculating is
no, tau 3 is the time spent in a given state. How long do I spend in each state? It is not, there is that average time spent in a given state. Yes. Yes. See, tau 2, why do I go to tau 2? Because I missed my slot, right? Therefore, best case my slot is the next coming slot, so I have to wait only 1 unit of time, or I have m minus 1 because I just missed. I have to wait for the entire duration of the frame, right, before I can get my term.
total waiting time. Then how will I do?
Total waiting time in the system itself. Okay. So the delay that we have here is so this will be minus 1. No, sorry. Yeah, because the actual transmission time is only 1, right? We did this before, right? We calculate the E of W and then plus 1 is E of R. So in this case, E of R is whatever you are getting, minus 1 will give you E of W. The waiting time is simply time until you get to the top of the queue. Once you go to the top of the queue, that means that it is your turn, right? So therefore, it will be this one.
Those are the waiting time that are there in all the states.
If you simply add tau and
All towns. These are the waiting times in all these states.
okay. No, but you also need to know the probability that you spend in these various states, right? The average packet might not simply have gone to S1, S2 and gone back to S0. Therefore, waiting time is simply 1.
Probability into waiting time.
So you are saying that use tau 2 as my reward function. I haven't tried that. Yeah, they're trying to say that you use sigma p1 and 2 again tau 1 again, right? Pi tau I, and then see if that gives me the delay. I don't know if that is going to work, but one can certainly try. Right? We can try that when we just do the implementation. Right? It's very easy to get this set of equations done. Whether that's going to be correct, so for a given packet I am spending time in this state with this probability. No, but the thing is it does not take into consideration the queuing aspects of it. See this when we try to do this E of R, right, equals n by mu and so on, that I have not really fully worked out, because E of R equals n by mu and n plus 1 by mu works. This is the similar thing you are asking for. No, I have to work it out. I am not sure if I can, whether that is going to be correct in all the cases.
Can agree for S naught, tau naught equal to 1 by beta makes sense that you can use the Markov model for it. But in the uniform distribution case for S2, how can you say correlate it to another Markov model where the states generally time spent in a state is like exponential in the Markov model, right? That is why we can switch to a semi-Markov model, but here it's uniform.
Okay, so the semi-Markov model is defined for the case where we don't worry about the distribution of the time spent, only worry about the mean sojourn times. That's what you're doing. So there is no necessary correlation to an exponential time. It is simply some random distribution for which we only know the mean time. That is the, and because they say that this works, that you can use the same approach to solve it. Is not there. So yeah, so it on the face of it, I mean, unless I go back and dig into some of the old books that talk about why this is actually this property, these probabilities are indeed correct, I love to do that. I have not really done that. Intuitively, it seems that we have expected memoryless property for the other two. In this case, we are taking any distribution, therefore where memory will be there in the system, right? That we can still expect these kind of results. But that is why if we look at my graphs, I was going to show you that I don't have the actual paper, but when what we normally do is I vary the load on the system, right? So this is my lambda and this is the delay, and then my analytical model will give me some perfect system like this. Then when I try to actually compute with simulation, for low loads I will always find that the values are reasonably close. For very high loads I am able to accurately predict, but here you will find in the knee how the curve will always find gaps throughout. That is because of these some of these assumptions that we are making. So if you really want to have the more accurate one, then go for more states, multiple states and the weighting stage. Then you will have no issue at all. Then there is no state which has got average waiting time, right? So S1 will be only 0 waiting time, S2 will be just 1 slot, S3 is 2 slots and so on, and that is very easy to generate. So if I had done that, then I would, in fact in my paper the other thing I did is I did not even go from S0 to S1. That paper will not have S0 S1 transition, it simply goes to S2. We simply say I arrive, I have to wait. Waiting time will still be m by 2, because if it's right, if you look at it, it will be m plus, actually it should be m plus 1 by 2, but my gosh, how many times I have figured out, I have tried it out, m plus 1 by 2 or m by 2, I finally just said m by 2, but that half slot will cause errors in your final simulation, because especially when the queue length increases, that will contribute to some more errors. So that this m, because okay, I just arrived, so therefore my waiting time is 0, or I just missed, therefore my waiting time is m, so it is m plus 0 by 2, it will again be m by 2. I said no, it should be m plus 1 by 2. So I have spent countless hours trying to figure out, but it is m by 2 finally is what I settled on. But I guess this was my first attempt at Markov modeling without knowing any basics of Markov chains. We just said here you give transitions, you give probabilities, the sojourn times, here are numbers. So we just took that on blind faith